Hi everybody. This is a little video giving an example using angular momentum to analyze a collision. So let's look at this problem I have picked out. This is a kind of a classic type of physics problem. We have a cart, it says, that runs into a rod that can spin, and then we're asked to find out what happens to the rod. Find the resulting angular speed of the rod is what we're looking for. I have a video to help you kind of visualize what's happening here, or I've created an animation, I should say. So we've got the static diagram, but here's an animation everybody watch. So here goes this object colliding with this other object that can spin, and that would be what's being described in the problem. We're going to watch it one more time and watch not only does the rod start spinning, but watch the blue object here in my animation slow down. And that's important to realize that, okay, well, comes in here, hits the rod, that would be a force acting on the rod, but then by Newton's third law, the rod would exert a force on the blue object in my animation, and that would slow it down. So that's what we would expect to happen to a cart that's described in this problem. How do we solve this problem? Angular momentum is the way to go. So we're going to write out this formula. Sigma L equals sigma L prime means the total momentum before equals the total momentum after, but it's the angular momentum, so L instead of P. We can't use linear momentum to solve this problem because the rod has an external force holding it in place. The center of mass doesn't move, so it does not end up with linear momentum as a whole. The rod stays in place. So we have to use angular momentum to analyze a collision like this, and then we just need to make some substitutions. The odd part about it is that the cart doesn't seem to have any spin to it, but we have a special formula for that. So here's this equation for finding the angular momentum of the cart, R cross P, which means cross product of position of the cart and the angular momentum of the cart. That would be its angular momentum about this same axis. So whenever we're using this conservation of angular momentum, we need a defined axis about which we're determining the angular momentum. So for the cart, we're just going to determine what is R cross P, and this is our reference for finding position is the axis of rotation of the rod. P1 and P2, the way I'm setting this up, I'm just letting that represent the momentum before and the momentum after. You could call it P and P prime if you wanted to. Doesn't really matter, but I just chose P1 and P2. But then we can make some substitutions for these values. Here I labeled it, by the way, just to make it clear that this is on one side of my equation. We have what happened before the collision, how much angular momentum was there. It was all in the cart. Rod was not spinning, so only the cart had angular momentum. But then afterwards, the cart can still be moving along the same line, and it would have some angular momentum as well as the rod, which would be spinning. So I omega for the rod is just a simple formula for the angular momentum of the rod. Momentum is mass times velocity, so I'll substitute that. And I have one other little detail. R cross P is multiply the perpendicular components. Well, R in our diagram is the perpendicular distance between the line that the cart is moving on and a line that passes through the axis of rotation. So that is our cross product. This particular R that's shown in the diagram times M times V. That would be true before and after. And then it's pretty easy to keep going and solve for omega. Omega would be the angular velocity or angular speed. And I've isolated I omega and factored out Rm. And then I'm going to divide by I. And then I made one more change. So our question said find the angular speed in terms of the change in speed. Change in speed, if you do exactly what that says, change in anything scientifically would always be final minus initial. That actually would be a negative quantity. So I've inserted a negative, so to speak. Change in speed would be V2 minus V1. And then in my expression here, I have v1 minus v2. So if I reverse that, I need this other negative sign. That's kind of a quirky little piece of this solution, but I believe that's the best way to answer this question, would be to include the negative sign to give the value, angular speed, in terms of the change in speed. We are sort of assuming that the cart kept going. Now, it's possible for the cart to bounce off, in which case this would technically need to be the change in velocity, not just the change in speed. I hope this solution makes sense to you. And this is what we were asked to find in terms of the given information, I and R and M and V. I created a follow-up example to kind of build on this. So this would be true for any collision like this. If you had the value of I, you had the value of R, and so on, then this should be a correct expression. But a lot of times you'll see a problem like this, you'll get more information. So let's look at this follow-up. Notice up here, I've included the result we already analyzed. I abbreviated it a little bit, but this we already figured out. But then notice what it says here. Suppose the rod has a mass equal to that of the cart, so same M, and I have a value of R in terms of the length of the rod. So I've added those in my diagram. So notice over here I put little r is now L over 4, which is pretty much what it looks like in the diagram, 1/4 the overall length. And then I, for a thin rod, would be 1/12 ml squared, and this is the same M. So I'm using the same symbol if that happened to be the case. Of course, that wouldn't have to be the case, but if that were the case, then this is what I would have for those quantities. And then I could take those and plug them in. So this is what I was trying to say a moment ago, that this should work for any particular situation like this, but now we have some details, so we can plug in those details for R and I. And then I would get this result. Omega would be given by this expression, which I can simplify. L over 4 has been inserted for R. 1/12 ml squared has been inserted for I. That's the rotational inertia of a thin rod. And then notice the m's are going to cancel. And then the 1/4 divided by 1/12 can be simplified and I'm just going to get a factor of 3 out of that. And then I end up with a pretty simple expression for the angular speed in terms of the linear speed. So that's kind of neat that I can get a result here. Whenever you get an expression like this, you should look at the units. Would I get correct units for angular velocity? Yes, because the meters would cancel. Meters and meters per second divided by the meters found in the length of the rod would give me 1/seconds, and that's equivalent to radians per second. You can also sometimes reason out, okay, does it just make sense? Okay, if delta V is bigger, would there be a bigger angular velocity? Well, that kind of makes sense to me. If there's a bigger change in the speed of the cart, there was a bigger force to cause that to happen, and that would make the speed of the rod greater. There would have to be a greater force on the rod causing it to spin. Dividing by the length of the rod in our final answer, so we have this final answer that shows an inverse relationship with L, excuse me. And that makes sense. If the rod were longer, it has greater greater rotational inertia. So kind of makes sense to me that it would spin slower if it has more inertia. Finally, I added one last extra bit to this. So let's look at the next slide. Notice now I've added one more piece of information. So I keep adding these little bits of information here, and what does it do to my solution? And the hope is that by seeing these variations, this would kind of cover a lot of bases, the types of problems you might see if you work examples like this that you might find in a textbook or a test or homework or whatever. So now I've added this, and the collision is elastic. So we're going to retain this L over 4 and the same mass as the cart, so equal masses. But now one more detail, and it's elastic. So an elastic collision is a special type of collision, and you can have an elastic collision with rotation involved. It means the same thing that it always means. What does it mean? I hope you know what it means. It means this. So here's A formula I can write if, and only if, I know that it's elastic, the total kinetic energy before the collision should be equal to total kinetic energy after the collision. So that's what I've got right here. Capital K, symbol for kinetic energy of any sort. So we have a system here. We've got the cart, we've got the rod. Each can have kinetic energy before and after. Well, actually the rod was at rest before, but either one could have kinetic energy if you're setting up a problem like this. So what does it look like in this particular case? Well, I've added a symbol over here. Let's again call this V1, like the initial value, V1, initial velocity of the cart. And then I'm going to write out a formula for kinetic energy. So here's a formula for kinetic energy. It shows the kinetic energy of the cart as simply 1/2 mv squared before and after. So V1 squared, V2 squared in those terms. And then the kinetic energy of the rod after the collision is 1/2 I omega squared, where it has been set spinning. That gives me an additional constraint, and it's actually kind of cool what can happen in a problem like this. If we know the initial velocity of the cart, and we know that it's elastic, and we have all this other information, we can actually determine what is the angular speed and what is the angular, or what is the linear velocity of the cart afterwards. We can basically solve for two unknowns: what happens to the rod and what happens to the cart. So if you write out this kinetic energy and substitute omega and I, so notice that's what I've done down here. I've substituted the quantity for I and the quantity for the angular velocity. And I've also put in V1 and V2. And then I get this expression. So I get this long expression here that shows a relationship between V1 and V2 that has to exist if this is going to be a kinetic a situation where the total kinetic energy is the same before and after. In other words, if it's elastic, then this has to be true. And if you do the math, you'll get these answers. Like you can show that V1, or I'm sorry, V2, the velocity of the cart after the collision, has to be negative V1/7. So that's going to tell us, oh, a negative sign, that means the cart would actually bounce off. An elastic collision is kind of a measure of bounciness. So if it's perfectly elastic, then the cart bounces off apparently. And then the angular velocity of the rod, or the angular speed of the rod, will be given by 24 speed of the cart before divided by 7L. That's kind of a cool result. Very particular result that has to be true. And you can check it yourself that those two expressions for my answer would satisfy everything that's shown above. So if V2 is equal to this relationship V1, then you could plug those quantities in here, plug in omega here, and show that that satisfies this condition. Angular momentum has to be conserved. And it also, if you plug in those expressions down here in our kinetic energy condition, it's going to satisfy both of those equations. So how do you get those answers? Well, algebra happens. Well, yeah, I didn't put all the algebraic steps here, but you can check either that those do satisfy the conditions, or do the algebra yourself. Better yet, get some practice. How would you simplify that kind of yucky looking expression I have there? It can be done. I'll give you a little hint. You can actually factor. That's kind of fun. If you like algebra and we learn how to factor, well, there's a reason why we learn how to factor. Sometimes it's handy. So that one's kind of neat. You can do some factoring to get that result, V2 equals negative V1/7. And then once I have that, of course, I can plug back in up here to get omega. So that's what I did. Here's what I got. I'm pretty sure these are correct because I checked them. And that's always a good idea if you have the time to check them. All right, so I hope this was a good example, help you understand how to do collision problems where you have a rotating object, one or more rotating objects, and we're using angular momentum to analyze the collision.